Hi, I'm John Oncea, Chief Editor of RF Globalnet, and since you're here, I think it's safe to assume you've maybe experienced problems predicting radio wave propagation and channel characteristics in complex 3D environments when designing wireless systems. Or maybe you're struggling with 5G, 6G, or Wi-Fi deployment, optimizing antenna placement, designing mobile device efficiency, or analyzing dynamic scenarios like mobile device movement in V2X communications. If any of this sounds familiar, you've come to the right place, as I'm joined by Ruth Belmonte, Wireless InSite Product Manager at Remcom. Wireless InSite is a predictive tool for understanding wireless coverage, channel multipath, and data through point for 5G, 6G, and Wi-Fi networks. Through advanced and accelerated 3D ray tracing and alternative fast ray-based methods and empirical models, it provides the tools needed to design wireless links, optimize antenna coverage, and assess key channel and signal characteristics for RF and MM wave frequency bands. Ruth, how you doing?
Good morning, John. Thank you. I'm doing well. Glad to be here.
Good. Glad to have you. Now, before Ruth begins, I want to let you know we'll be holding a Q&A after this presentation, so please feel free to submit your questions as we proceed. We'll address as many as possible during the live Q&A, and if we can't get to you, we'll reach out to you after the event. Just a bit more housekeeping here. If you run into any issues, please try to refresh your browser first. If your problem persists, submit a question via the Q&A, and we'll help get you back on track. Finally, and lastly, today's presentation will be available on demand within a couple of days, and you're going to receive an email with the link. With all that out of the way, we're going to turn things over to Ruth.
Well, good morning, everybody. Happy to be here. We're going to be talking about how Wireless InSite can be used to do RF, to model dynamic RF scenarios with its new mobility features and some of the capabilities that are part of this new release that also can be analyzed. So just to give you a quick overview of what we're going to be talking about. I'll give you some context regarding Wireless InSite and Remcom's tools in general, and then the new mobility capabilities that are part of Wireless InSite, the multi-frequency broadband capabilities that are useful for some of these dynamic scenarios. Then next I'll move on to our unique hybrid EM capability, which takes full wave analyses from XFDTD and brings those results into a ray tracing simulation and lets us combine the fields and ray tracing via Huygens surfaces. So that's a unique capability that I'll spend a little time talking about. And then last, I'll move on to our lunar propagation support. So the Wireless InSite, enables people to bring in terrain, define materials, etc. So then we'll have a little time for questions like John mentioned. So just some background here. Remcom has three main products. The flagship product is XFDTD, which is a full wave solver based on Maxwell's equations, typically used for antenna design, device design, EM scattering, also for some bio-EM like star calculations, RCS, etc. Wayfarer is our newest product, and it is used for sensing, radar simulations, RCS, etc., indoor, outdoor, chamber type simulations, etc. And then lastly, what we'll focus on today is Wireless InSite, which I'll get into some more detail, but specifically our 3D GPU ray tracer, etc. Let's see. Yeah, so Wireless InSite specifically is a suite of propagation models and comm system post-processing tools that support a variety of use cases, environments. The models are validated, deterministic. Our 3D ray tracer is GPU accelerated and very applicable to both urban settings, outdoor, indoor, combined settings, Supports MIMO, has post-processing, like I mentioned, for beamforming, spatial multiplexing, diversity, antenna diversity, etc. Also, appropriately has extensions for millimeter wave and diffuse scattering, so support for, you know, a broad range of frequencies here. Applications are wide-ranging, 6G, 5G, SINR and throughput calculations, etc. The models generate and provide users with detailed path data. So arrival times, arrival angles, powers, fields, etc., can be exported and generated for all of our results here. And that makes it a very useful tool in digitized RF system analysis. So if you want to do channel emulation, if you want to replace measurement with simulation for, you know, you don't have enough, you can't go somewhere. Let's say you're going to the moon, right? Well, you can't just send a team up there to do measurements whenever you want. You can do simulations. You're designing a new system, something that doesn't exist yet. So this can replace measurement. It can be fed, the results can be fed into channel emulation tools. Or you can generate, you know, a lot of data for machine learning, synthetic data for machine learning, developing systems that are supposed to understand sort of the channel, the RF system channel of an environment or a variety of environments. Now, specifically, the new capabilities for mobility, I'll highlight next. So Wireless InSite's mobility the concept takes what we call mobile platforms, where the user can assemble geometric objects, you know, vehicles, UAVs, human beings, etc., and transceivers, either transmitters or receivers, both that have a specific physical relationship to that geometry. And then you move that assemblage through the scene, defining its waypoints, its speed, its orientation, etc. So on the right here, you see a UAV in multiple positions as it moves through this urban scene. The results are also visible, showing you the paths that are found between a cell tower and a mobile UAV drone moving around. So yes, the Wireless InSite will generate results for each of those steps that you've defined, and you can visualize them or plot them, export them at each time step, for each time step. This just shows a little bit closer how an object here, a human being and a transceiver, a handheld device, are both brought in together and visualized in relation to the platform's origin. And also you see how it's oriented here. All of this can be changed. You can move each part separately or rotate it relative to the platform's origin, get it how you want it. And then here on the right shows the 2D editor where you can place waypoints in a visual way, clicking sort of through the 2D project view here. All of this is editable and changeable. You can also have things already defined and bring them in together. If they've already been defined in a static scene, you can select items that come in together and are placed together on a platform. Waypoints are defined and shown to the user here, just with a constant speed. But there's a lot of options. You can also bulk edit and define a whole lot of waypoints, just bringing them into an editor. You can also define time-based waypoints that would be useful if you were trying to show acceleration or some sort of changing dynamic velocity. The sampling rate is editable and changeable in the study area. So when you're defining your simulation, X3D is the model you also need to define what is the time interval at which you want to sample your scenario. Units or seconds, but you can choose whatever you would like, and this will definitely affect how many runs you're going to need to make under the hood. Wireless InSite will calculate, okay, you want to sample this so often, the things that you've defined are moving this way, that will take so many simulations. And it's important for the user to probably see, okay, how many steps am I defining here? So that's also something that can be previewed when you're looking through the platforms. You can preview for each study area you've defined. You can sort of see, okay, that's a total of so many steps. And you can decide whether you want to downsample just as your first run, just to see how things are moving. You can also preview in the geometry view how things will be situated at each of those steps. So this is a useful sort of preview before you run, before you determine exactly what your steps should be or what you'd like them to be. You can have a little bit more information that way. This image here on the right shows a mobile scenario where there's two platforms. There's a human being, which is maybe a little hard to see, moving down the street, and it starts here. You can see the person moving, and the person has the handheld device and trying to figure out where their car is. The car has a transmitter here, up at the top here. And meanwhile, there's a different platform. There's a moving bus that's coming along the street here, and at some points interrupts the connection between the car and the person, and other times enhances it. You can see these paths change quite a bit as the bus goes through, as the person moves through foliage, behind little tents, etc. So this is showing, this animation can be made in Wireless InSite after the simulation is run. You're seeing the paths for every single time step, and sometimes that's nice. You can see how dynamic the situation is. You can also plot results versus time. So this shows you here on the right a blue and red plot. The blue plot shows the results that I was just showing you for that scenario when there is no bus. So you don't see any major dropouts. You do see the person before it's coming around the corner. There's a lot of dropouts. And then there's some enhancements and a little variation due to the foliage, the little tents, how different buildings diffract, etc. Now, when we added the bus, now you see some dropouts when the bus passed by, but you also see some enhancements. So that situation, based on how dynamic the scene can get, can really vary over time. And that's part of what this mobility capability will allow people to analyze.
Hey, Ruth, can I just jump in here real quick?
Sure.
So that's a lot of information and a lot of examples. So why is all this important? What kind of problems are we solving here, and how is this helping?
Well, if you're designing, let's take, a fob or some kind of, find my whatever, find my keys, find my car kind of device, you might say, well, these antennas work great when we're just in a chamber or in an empty environment. But when you start to think about how is that going to behave and perform in a complex environment, you might say, okay, well, let's put it in a city scene. All right. You do that once and you have a city scene, but you still don't have a sense of how it can vary as the person walks or as the city environment changes. And that dynamic aspect of real world situations is just, it's a reality. So even if you just look at this plot, for example, these deltas, they might not look large on this plot, but if you look at the scale here, that's 25 dB, 30 dB changing. And even if you ignore these dropouts, 40, 50 dB in some cases. So a engineer would want to understand how variable that can be, and they'd want to even investigate, even changes in how the person is oriented, or how the antennas on the hand are oriented, and that's all things you can do pretty easily now with mobility. And here you're looking at, how many steps did we do? Many steps here, and 72 steps, I guess, for this scenario, and that's 72 different pieces of data just right there, and that's just one simulation. So anyway, that might give you an answer. I hope that helps.
Yeah, and I don't want to bog you down, so you could just answer this yes or no. But is it possible to set up like custom flight paths and import waypoints?
Yes,
Is that something
so in the previous slide, I think, or a couple of slides ago, I showed these waypoints here. You can enter them either graphically or, entering numbers one by one by clicking into this field here. But you also have a bulk edit option, which if you have a text file that has all the data that you'd like, your XYZ locations, plus any orientation changes or time steps, you can just copy that in as a bulk edit. Yes.
Okay, thanks.
All right, so moving on, I'd like to talk about multi-frequency and broadband simulations. So the benefit here is that now a user can define a single project that is a valid project over a range of frequencies. Wireless InSite is a physics-based ray tracer. So when we calculate the fields on every single path we find, or even the paths themselves, we are looking at the geometry and the material properties of that geometry. So if you're running at a specific frequency, we need to know the permittivity, conductivity of that material, even the surface roughness of that material at that frequency. And now with multi-frequency materials, for one thing, we can define those properties over a range of frequencies. We also support multi-frequency antennas. These can be measured in the chamber and then brought in as pattern files for specific frequencies. They could be simulated in a tool like XFDTD over a range of frequencies and brought in again those patterns for each frequency. And you don't have to say, oh, each of these patterns is a different antenna. What you're saying is this antenna behaves in these ways over these frequency ranges. So that simplifies things. You have one antenna definition that's valid over a range of frequencies. You have one material definition that is valid over many frequencies. The atmospheric effects have been built into Wireless InSite for years, so we'll talk about that a little bit. But again, as you go up in frequency, those attenuations are going to be accounted for. And then lastly, I'll mention that for MIMO antennas, we have frequency-based S parameters that are able to be defined, and then you get that change in behavior of that MIMO system as the frequency changes. You define those things, and then as you run your simulation, you don't have to keep changing what's active or what's being used, because the frequency at which for every frequency you run, you are going to take the correct thing into account here. So that simplifies everything by just having a single project. And then optimizations of this are based on, we only need to do the ray trace once. We ray trace, we find all these paths, and then that EM calculating the fields for each of those paths is done specific to each frequency that's been run. Okay. We also have some broadband analysis tools, utilities that are available separately from Wireless InSite that allow users to benefit from this broadband analysis, calculating broadband CIR or frequency spectrum, etc. So just to show a few examples, here's a multi-frequency antenna that was simulated in XFDTD. It actually represents a MIMO antenna that's valid over a range of frequencies. So what Wireless InSite brings in is the pattern for each element and for each frequency, which you can then view and look at in this table. But it is defined as a single antenna in Wireless InSite. Wireless InSite doesn't have to create, maybe 20 different antennas here. It's creating one antenna, and then it selects the correct pattern depending on what's going on, and the correct element, of course, since it's MIMO. This just shows you the attenuations, typical, people are familiar with, probably at 22 and 60 gigahertz for water and oxygen. So that gives us a good assessment of, the impact of the atmosphere on attenuation over a broad range of frequencies. The user defines temperature, pressure, and humidity. So once those are defined, specific attenuation can be calculated for that frequency. This just shows you how the multi-frequency materials look in the tool. The user will define for each frequency all the electric properties that Wireless InSite is expecting: permittivity, conductivity, surface roughness for that top layer of the material, and do that over a range of frequencies. Like I said, this then is a single material for all of those ranges of frequency. And then when you actually run the simulation, you put in your frequency sweep. You give a range of frequencies, a start and an end and a count, or a start and an increment and a count. And then Wireless InSite does the ray trace once and then assesses the behavior for each of those frequencies. We are going to be extending this to support a list of frequencies as well, which I think most users would like to see. So that's coming soon. Okay. Here's an example of an indoor house, a connected house with various devices running at multiple frequencies. So we ran this, and we're looking at the results over quite a range of frequencies. What we see here on the top is the results plotted. We picked out the results over this whole range of this route of receivers. For 2.4 gigahertz is the red, 5 gigahertz is the blue, and the green one is the 6 gigahertz. So you can pick out specific frequencies to plot. You can also do some statistics. This middle plot here shows the mean, max, and minimum power at each of those receiver points. So this is aggregating over that full range of frequencies. And then this last plot here, just we chose a single point and said, how does that point, how's the power at that point going to change as we go through this range of frequencies? So you really have some access to the data. You can look at it the way you want to in terms of plotting. And then over here just shows the power at each point for a specific frequency. But in the UI, you can actually animate this if you want to. If you wanted to see how this changed over frequency, you can just do that, sort of like what I showed with the paths earlier, changing over time steps. You can also look at data changing over frequency.
Ruth, let me give you a break here. I'm going to ask you another question.
Sure.
As you're talking more and more, I'm realizing how little I know, but we've got an audience full of engineers who are a little bit smarter than me. This to me seems complex. Is it as complex as I see it? And is there any kind of training and support that will come in case people get bogged down?
Okay. Well, Wireless InSite itself, does have a learning curve. The new features have their own learning curve because there are a lot of changes in this release. So how do you look at results? How do you access, because now you have much more access to looking at, like I said, frequency-based outputs, time-based outputs. So there is a learning curve here. Wireless InSite and RIMCOM are very devoted to helping users. We love solving problems. We love solving hard problems, and we love helping our users, understand how to use our tools to solve their problems. So we do have trainings. We have a good tech support team, and yes, when you buy Wireless InSite, you do get there's multiple levels of support you can ask for, but and pay for. But yes, anybody who buys it will get the support they need to be able to run and solve the problems they need to solve.
Okay.
Yeah. All right.
So I wouldn't be lost. Cool.
No, you wouldn't be, and it's fun to help people learn how to use this tool.
Thanks.
All right. Yeah, we'll move on to the hybrid EM. Like I said, this is unique feature REMCOM is providing here. I don't believe anyone else really has a solution like this. So what we do here is we have used Huygens surfaces to bring full wave analysis into the ray tracing environment. When I mention Huygens, I'm referring to Christian Huygens, Christian Huygens, some people might say, who this is named after. Of course, there's been a sequence of mathematicians and physicists since then who've really developed this concept. So from Huygens to Fresnel to Lorentz to Stratton and Chu, and the concept is you take in our case, a small device, let's say, which is represented with CAD, the printed circuit board, the antenna are all represented here. And in a full wave solver like XFDTD, you capture the fields from that are interacting in the near field with this arm, in this case, this wrist, this fingers, all these things that are inside this surface. And you capture the fields on that surface. So we're looking here at the CAD being represented inside this surface here on the bottom left. And the concept of the equivalence principle and reciprocity is that the fields here on this closed surface can be used to find the power transmitted either in or out of this surface. So we use that and we bring these fields into Wireless InSite, where we can then do the ray tracing and combine that with the fields that were found in the near field to do a accurate calculation of how the larger environment is interacting with this smaller scale near field device. The tools involved are, like I mentioned, XFDTD, one of REMCOM's real flagship product here. And we use that to capture the near fields and then bring them into Wireless InSite, where the larger environment can be simulated. So examples would be, a GPS on a hand, a watch to a GPS satellite, very long range. Access point on a body to devices in a room. You may have an AR device or other, Bluetooth devices or something else. Wi-Fi all inside a room, or you may even have body on body. So devices like earbuds to your watch, earbuds to your phone in your pocket, etc. So all of those can be simulated using Wireless InSite when you want to also be sure to capture the near field behavior near that body in this case. REMCOM and Wireless InSite make this import very smooth. We have a seamless import capability, export-import from XFDTD into Wireless InSite, where once you've run your simulation in XFDTD, you capture your fields with XFDTD with these surfaces. And you want to make sure that you are maintaining the physical relationship between that body and the fields. if you bump that around, if you move these fields around, you won't have something that's consistent with the physical thing you've simulated. So it's important to bring these in as a package with respecting and maintaining the physical relation between everything here. So that's done using this platform package. The platform package is very similar to what I already described for mobility. You are bringing in an assembly of geometry and transceivers that you want to maintain their relation to one another. So that comes in as a platform that you can decide whether to move it or not. You can keep it static, or you can move it around an environment. It also brings in the basic material properties of that object. So it makes it simple for the Wireless InSite user. You don't have to, specify transmitters and receivers in some, trying to align that in the same way. Here's an example of a watch, on a hand that was simulated in XFDTD and brought into Wireless InSite. This is a close-up of the GPS rays coming, reflecting, diffracting around this body, and then coming into the watch. And then on the left here, you see the very large scale rays paths coming in from the satellite, interacting with different parts of the city as the person is moving inside the city. You don't really see what's happening. You can't see the person, but you do see the paths changing. And then here on the right, you can see the person moving about 60 meters downrange, closer to, our viewpoint here. And you see those paths coming in as well here. Another example, here we have the person holding the arm in different positions. So you have the what time is it pose, and you have the walk hand back pose. And both of those are then brought through the city scene like I just showed you. And you can see how it varies, how the signal, received power to the watch changes as the person moves, and how it varies between these two poses. And we're looking at, 20 to 30 dB differences across this set of points here. And this is the phase here on the right. And the last example I'll show is the body to body. In this case, we're looking at this blue line here shows what results would you get if you did the entire simulation in XFDTD. Keep in mind, for a full wave solver, this is a large problem to solve. You're taking in the entire body and you're doing this entire simulation all in XFDTD. Alternatively, you do what I'm kind of showing here in these images, where you've done you've just captured the signal around each of these devices in XFDTD. You've brought them into Wireless InSite, and now you're doing a simulation in Wireless InSite. So let's look at some of this. The results, if we look at the the watch to the earbud, we can look at the S12, S21 values calculated in InSite and XFDTD, and look at the deltas here. The deltas are 1 dB-ish, a little bit less sometimes, a little bit more sometimes, but very close. Same with the watch to the left earbud, so both directions, very similar. But if you look at the run times and the resources required, trying to do this whole thing in XFDTD would take 203 hours and 160 gigabytes of GPU RAM. So that's a lot of resources. While if you do this hybrid technique using the Huygens surfaces, you still need to do some work in XF, but this is the total runtime, total GPU resources here. So you're really reducing it. Total runtime is now 6.5 hours. Resources have been cut by more than a tenth of the resources are required. So this hybrid approach really expands the use cases that can be captured here. Really, beyond, and this is still a simple case, but you want to do a city, you want to do something much larger, or even a large room, or even a small room. This is just 2 walls here. Those would be computationally prohibitive to do purely in XF or any kind of full wave solver. So the hybrid approach really allows you to take these devices into complex environments and still analyze their behavior. All right, that's what I have on the Huygens. I think we're going to move forward here.
Before we do, real quick, I'm really looking forward to the lunar propagation. That's the highlight of this for me. But the more you talked about Huygens, the more interested I got in that. And there actually might be an article coming up on Huygens. But my question specifically here is, when would it make more sense to use a Huygens surface than, instead of like a far zone antenna?
Yeah. So anytime you want to capture the near field effects, like I said, when we do this full wave simulation in XFDTD, you are looking at how that wristwatch, let's say the smartwatch, antennas, all the geometry of that thing, the materials of that device, they interact with the wrist. They don't perform the same way in a vacuum as they do when they're on a body. So when you want to capture those near field effects, that's important. Also, when you want to capture them while also capturing the geometry of that person, you want to have that whole person in your scenario because, there are ray paths that are hitting the person, diffracting or reflecting off the person, being blocked by the person. And so you want the geometry of the person and you want the near field effects. If you used a far zone pattern here, number one, you wouldn't get the near field behavior of the wrist. If you had a far zone pattern that included the wrist, you wouldn't have the blockage of the wrist. You might double count the blockage of the wrist. So you may end up, having some difficult physics, consistency with reality if you did that.
Okay. And I think we're good on time. I'm going to ask another one real quick,
Okay.
and then I'll shut up. So how does Wireless InSite integrate with Huygens antenna data, and why does that matter for accuracy in the near field?
Okay. So like I mentioned a couple slides ago, we have this platform package, we call it. And XF will take you, after you've done your simulation in XF, you can select the geometry and you can select the results that you're interested in importing to Wireless InSite. Okay. And you export that as a whole package. And that is important because when you bring it into Wireless InSite, you are ensured that the placement of those fields relative to the geometry is maintained. It is the same as what it was when it was simulated. So the physics is consistent. The location and the placement of these fields relative to the geometry is very important. You would get discontinuities if you tried to do this by hand, it'd be very tedious to get all of this right. So this integration we have makes that precise, and making sure those fields relative to the geometry are accurate is very important.
Okay.
Hope that answers your question.
Oh, it does, as much as you can for an old journalist.
I guess I had one more slide on the Huygens. This is just, a summary slide here, just highlighting that the workflow is, the simplified workflow captures the near field accuracy that you would get in a full wave solver like XFDTD, but it's inside Wireless InSite ray tracer, which gives you that benefit of really being able to extend the scene that you're trying to simulate. The platform antennas, all of this allows you to do an electrically large scene and reduces the hardware and runtime required. So that's all I really had on Huygens. I guess we're going on to lunar now. That's okay. All right. So I've mentioned this before. Wireless InSite is physics-based. You give it inputs, you give it geometry, materials, frequencies, antenna patterns, etc., and it will ray trace in that geometry do EM calculations based on the material properties and the antenna properties, and provide outputs. This means that it really has always been able to pretty well capture lunar propagation. What we've provided most recently is real improvements to how to import the data. So our GDAL terrain importer now is extended to understand and recognize projections for the moon. And so now when you bring in those data sets, they are properly set up and oriented. The coordinates are transformed properly, so the systems on the moon are placed properly. Also, Wireless InSite, when it recognizes that you've brought in a lunar scenario, or if you tell it it's a lunar scenario, it will automatically set the pressure, temperature, humidity to vacuum, so that it's appropriate for the moon. You won't get those attenuations at 20 and 60 gigahertz. Because the oxygen and the water vapor is pretty, not there. And then lastly, we do have a built-in lunar material database. So there won't be any guessing as to, well, how is the regolith material defined? We provide that to the user now, which makes all of this, pretty straightforward. Like I said, importing the lunar terrain, it's just our GDAL our GDAL importer. It reads the metadata and it will know, okay, this is a lunar projection here. And then when it comes into Wireless InSite, you'll see the curved surface. If you get a large enough piece of terrain, you'll get the curvature of the moon in Wireless InSite. There are a few things the user would have to pay attention to. One is that it recognizes that it is the moon, a projection of the moon. That's written here. If it's understood, some data doesn't have that very well recorded. So if the user knows they want to be using the moon, they can override and say, if this is a checkbox here, that they can override, and then they can set this to lunar. If you don't do that, if for some reason the data set doesn't know that, Wireless InSite won't know this is the moon, and it won't set the vacuum, etc. So you want to make sure of that. But once that's done, then the projections and the temperature, pressure, humidity, et cetera, are all automatically taken care of. The database for materials we have includes almost 200 materials. And this is based on a range of frequencies and a range of different regolith depths, and as well as a range of mineral content for the titanium and iron that are typically found in regolith and in the bedrock. So all of these things are varied, and about 200 materials are automatically, we've already generated those materials. They are part of a database that is loaded by the user and then can be applied either, you can choose a default, or you can change any scenario to use any one of these materials. Here's just some examples of lunar propagation. This is very rugged terrain on the moon. You see variations that are much more extreme than you do on the Earth. So getting into craters and the 3D behavior of propagation in a crater is very important. You also have dropouts sometimes when signal can't get down into a crater. So understanding that propagation is definitely something that's of high interest these days. Talking about different missions, specifically to the South Pole of the moon, where these craters are quite rugged and deep. So this just shows some of the propagation we've done, field coverage and ray paths, where you see reflections off of various parts of the crater. I think I have a video next. Hopefully it'll actually show. I don't know if it is. Once you go live, there you go. I think you should be able to start to see. This is just tracing, but tracing a path from through this crater, so that you see how the ray paths vary from point to point as you move through that crater. They're scattering from various parts of that bowl. So REMCOM is supporting NASA. We have several contracts with NASA, ongoing and upcoming, to better support all of this work. It is compatible with mobility and with the Huygens surfaces. So we have ongoing work to provide the user the ability to vary these different inputs to the material generator. Like I said, we varied the things I mentioned, but a user may want to do other things. So that's upcoming. And we're also improving the 3D ray tracer. So that we can better get into these deep craters. We have a GPU enhancements to the ray tracing that will include reflections off of curved surfaces, surface waves, and other enhancements to better capture, let's say, the diffuse scattering from, the regolith materials, which are really, complex, with various size rocks and dust sort of all striated through these materials. So that work is ongoing. I think I'm concluding here. Yeah, I can summarize that Wireless InSite itself, as a tool, as a product, includes validated deterministic RF simulation models that are valid in arbitrary environments. It provides accurate, detailed path data that can be used in various ways, like I've mentioned. The path data includes polarization, the antenna gains, phase data, etc. Mobility allows now the definition of motion for configurations of objects and transceivers in an environment, any environment, and then provides time-based results for those configurations. The multi-frequency analysis capabilities allow a single project to be defined that is valid over a range of frequencies. So a single project now can work in many, many different frequencies. And then the ray tracing itself is optimized because you do it once and then calculate the fields and results for each of those frequencies. It reduces runtime and it reduces the time it takes to set up a project or switch projects. The Huygens antennas provide a unique ability to get near field accuracy of a full wave solver in complex large scale environments using ray tracing. This improves runtime, has a much smaller resource footprint, and really allows analysis over a broader range of frequencies because the full wave scenario can be kept small. And then when you move on to the larger environments, you're not as dependent on frequency. You're no longer using a frequency dependent a system that gets electrically larger as frequency goes up. So that you've sort of isolated the parts that can get more complex due to frequency. The lunar propagation capabilities provide terrain imports and material database built in so that the user isn't spending a lot of time trying to figure out how to represent the lunar environment. And then the ray tracing for lunar environments is, like I said, the optimizations are in the works and improvements are in the works, but currently, the Wireless InSite X3D GPU ray tracing is a lot, the best one we have for that environment. I think that includes my talk. I'm certainly open to questions here.
You got 10 more minutes, Senya?
I do indeed, yep. Mm-hmm.
All right, before we ask you the first question, there was one asked earlier, how much simulation time for this scenario? I don't know what scenario that's referring to. It was like about 11:15. So if that listener wants to tell me which scenario they're referring to, we can ask that question. I got another question here.
I'll answer just generally. The simulation time can vary quite a bit. So if we take one single time step and we talk about an urban scenario like we saw in the mobility discussion. The runtime will depend on the interactions you're allowing. So if you really just want to get a very quick run, you can say, just show me the line of sight results. You can say no interactions, and it will run extremely fast. I mean, we're talking about just a few seconds to calculate, well, what's visible line of sight. But most of the time you want to see a little bit more. I mean, we talked about all these interactions of buildings and the EM we're doing. So you add reflections, you maybe add one diffraction, the runtime's going to go up. Runtime will depend quite a lot on diffractions. Those cost a lot because every time you diffract, you're basically doing a new ray trace. But I would say anywhere, like I said, from seconds to, if you're doing, many time steps in a dynamic scenario, it can take a few hours. It'll also depend on how many receivers you have. So there are a lot of things that impact runtime.
And I bumped your slide up there so that the listeners, the viewers, have your contact information. If they wanted to reach out, they can grab that. So the lunar propagation, how well does Wireless InSite manage unusual environments like lunar surface comms in obstructed areas?
Well, I've mentioned that Wireless InSite is sort of agnostic to what the environment represents. As long as the user brings in accurate terrain data for the moon and defines the materials in a realistic way, then Wireless InSite really doesn't care that it's the moon. I mean, it's doing its physics. So we've provided the GDAL import for getting the elevation data in there correctly and represented correctly so that it's, projections make sense, et cetera. We've provided a database with almost 200 materials that represent regolith, different combinations of things for regolith material. So both of those parts of the problem should be made easy now with what we've provided. And then the last part of that question is, obstructed environments, the deep craters, et cetera. X3D, our main propagation model in Wireless InSite, does a pretty good job. I think I showed some ray paths getting into that crater. But like I said, we're currently working on improvements to that. Being able to do reflections off curved surfaces is important because we can miss reflections sometimes if the terrain is very facetized. And also just creeping wave, getting over a surface into a crater is something that's also challenging. So both of those are what we're working on right now to improve the ray tracing for that kind of deep crater type situation.
Okay. Here's another one. What users can access mobility?
We've made mobility.
What users can access mobility?
Yeah. We've made mobility available to any level of Wireless InSite purchase. So even with, sometimes MIMO is I think the highest level of Wireless InSite, costs the most. But even if you buy the basic level, you'll have mobility. We consider it an essential part of really any kind of analysis nowadays.
How about what sets Wireless InSite apart from traditional drive testing or field measurements?
Well, I would say that one thing that sets it apart is you can do it on the moon, for example. You don't need to actually set up and be able to set up devices and equipment to do these simulations. And that really enables people to, number one, understand how something's going to perform before they build it. You may be looking at some sort of indoor devices, like let's say AR gaming or something where you have some devices communicating with other things in a room. Well, depending on the layout of that room, that device may really perform well or not well, or the orientation of somebody that may affect that. And how many different things do you want to actually measure? That's hard. That's time consuming. Whether you're going to go build 500 different houses, you can simulate that instead. So synthetic data generation is a really wonderful thing that Wireless InSite can provide. Running simulations in environments that you can't get to, like the moon, that's something that Wireless InSite can provide. And so those are things that would replace typical measurement or other things like you asked, drive test.
I don't think we answered this, or you talked about this one. Can path data be used for channel emulation?
Yes, in fact, it's definitely something users want. We have the ability to export to Keysight's PropSim and also Spirent's Vertex. So that is something users have asked for, and we definitely would like to support. The path data is very, provides a more realistic type of input for those tools. So yes.
Okay, cool. How can engineers leverage Wireless InSite to design and validate 6G and next-gen systems before deployment?
This is similar to the answer I think I just gave. Since Wireless InSite is physics-based, there are no preconceptions about what systems are deployed. There's no assumptions about what antenna patterns are being used, what polarizations, what frequencies, or even what atmospheric conditions or material properties. So the user can define, the engineers are able to sort of imagine what they want and how they want it to behave, and then test them before they're made. One example was a few years ago, we developed these electrically engineered EM surfaces, which are basically meta surfaces that can be used to redirect power, or EM power propagation in an environment. Before deploying that, people wanted to understand that, so we have that capability built into Wireless InSite, and as that keeps, if that develops further, people can simulate that before they build it and see how well it actually can be used to affect the environment. So,
okay. Let's see if we can squeeze in one or two more.
Okay.
What upcoming features or enhancements are on the roadmap that you think will be most impactful?
Well, the next release we plan would have this, what we call it, antenna rerun. So right now, when Wireless InSite does a simulation, the antenna pattern for whatever frequency is already defined, and it's defined once, and it's used to calculate the fields and paths and power and everything that arrive at the receiver. We will have this ability to swap out antennas and not have to do the full ray trace when you want to see, well, how would the antenna behave if it were either oriented differently or if it had a whole different antenna pattern. So that's a capability that we released as a beta to specific customers over a year ago. So it's getting pretty mature. We're planning to release that next. So that's going to really improve the ability to do simulations for larger sets of situations very quickly. Other things would be just improving the export process for channel emulation tools like PropSim.
Yeah. All right, I want to squeeze in one more because I want to know, this is one I was curious about too. Can the new mobility capability capture the motion of multiple people or vehicles in time?
Yes, so you can have an arbitrary number of platforms. Each of those is independent in terms of its route, its velocities, orientations, what geometry is on it. You could have several people, you could have vehicles. I had in my scenario one person and one bus. Those were two platforms moving independently from each other. But yes, you can have multiple. You can have a UAV flying around up overhead, etc. They're all independent.
All right. I said one more, but I lied. I got one more. First of all, Rodrigo out there told you, thank you very much for your excellent presentation, and I second that. The other question was, Is there any integration flow to support channel modeling between TX, RX with dynamic antenna switching or tuner states?
Okay, let's see. Um, I would say that it sounds to me, if I understand the question, it sounds like our antenna rerun would support that. Not sure if I understand the question fully.
Yeah, so let's just back table that one and
Yeah,
to the
antenna
person who
switching,
asked it.
that would definitely sounds like the antenna rerun that we're talking about.
Okay, well, and that kind of rolls up here into my conclusion. Any questions that we didn't get to or we couldn't answer, we'll get back to you. Ruth, thank you so much. I really appreciated everything you did. I'm fascinated by that picture above you. I'm trying to figure out exactly what's going on there. But thank you so much for everything you've done. And thank you all who attended. If you want any more information, you can visit the website or reach out to the team directly. Everything there is in the last slide. And as a reminder, we're going to be sending out a recording of the webinar shortly, as well as reaching out directly to the questions we couldn't get to. Thanks so much for everybody joining us, and we look forward to seeing you in future sessions.
Thank you, John, and thank you, everybody.